We're now ready to move on to drawing some more complex Lewis structures, and we'll also be introduced to the idea of resonance. So simple Lewis structures for molecular compounds are pretty straightforward to draw. And you can use the technique of drawing arrows to pair up the unpaired electrons. So for example, when you have an H and a Br, you have a single electron that can move to pair up with that single bromine, and then you have a bond here. Two single hydrogen atoms with their own valence electron can form two covalent bonds with this sulfur because this has two unpaired electrons. So you can imagine an arrow moving like this, and now you have these bonds here. So how do we predict Lewis structures for these complex molecular compounds? Well, there's some of these guidelines. They aren't really rules, but they are pretty well followed. So the first thing you want to do is you want to write the skeletal structure. The H atoms are always terminal. That means they're always on the end. And the reason for that is that hydrogen can only form one bond. So it has to be on the end. It can't form two. You usually put the less electronegative atom in the center. Not always. Obviously, if the hydrogen is the less electronegative, it cannot go in the center. So this takes precedence over this. So as an example, silicon hexahydride. So you have silicon in the middle, and then you have the H's that go around it. So here we have our silicon, our hydrogens, and then you calculate the total number of electrons for the Lewis structure by summing all of the valence electrons. And then if there is a charge, you will need to add or subtract electrons to account for those charges. Okay, so it's quite the process. So you'll want to go through this slowly until you get comfortable with how to do these. And if you need more practice, check the extra practice problems. So silicon is 4 valence electrons per atom, and there's 1 atom, so that means there's 4 valence electrons. Hydrogen has 1 valence electron per atom. There's 4 atoms, so that's 4 valence electrons. So our total here is 8 valence electrons. This compound is not charged, so we do not need to add or subtract any electrons to account for the charge. So once we've done that, we can distribute our electrons among the atoms, making sure that we have our octets. So we want to draw a single covalent bond first. If we can't get there, then we can form double or triple bonds. So by that I mean if we don't get an octet and we run out of electrons, we're going to use double or triple bonds. So let's come back to our silicon tetrahydride example. So we have 8 valence electrons, and here's our skeleton. So we put in our electron pairs. These are our bonding electrons. And you'll notice that we have distributed evenly all 8 electrons. So the last thing that you want to do when completing your Lewis dot structure is to take these bonding pairs, and instead of leaving them as 2 dots, you want to make them a line. Now if it's a lone pair, you don't make a line. Lone pairs are 2 dots. Bonding electrons, bonding pairs are lines. Okay. Now we have this complicated structure that we'll have to figure out. For some compounds, there are more than one way to draw our Lewis structures. So when they have the same skeletal structure but different electron arrangements, that is a resonance structure. So for example, ozone. You could imagine drawing ozone with a single bond between these 2 oxygen atoms and a double bond between these 2 oxygen atoms, or you could imagine putting the double bond over here and the single bond over here. Now, experimental evidence shows us that the actual compound looks like this. which means that both of these are contributing equally to our compound. Okay? So we can double check that this is drawn correctly by counting our electrons. So remember that oxygen has 6 valence electrons and there's 3 of them, so we need 18 total. 2, 4, 6, 8, 10, 12, 14, 16, 18. So we have enough, and we notice that this oxygen has an octet with 2, 4, 6, 8. This oxygen here has an octet with 2, 4, 6, 8. And this oxygen here has an octet with 2, 4, 6, 8. Now let's predict the Lewis structures with all resonance structures for carbon dioxide. So this is CO2. So if you'd like, you can pause and sketch out your Lewis structures and then see if you are correct. So again, our guidelines, we're going to write the skeletal structure. We're going to calculate the total number of electrons. We're going to distribute our electrons among the atoms, and then we will add double or triple bonds as necessary to get to our octets. So here we go. We put our least electronegative atom in the middle, so our carbon is in the middle and we've got oxygen surrounding it. We know that carbon gives us 4 valence electrons. Oxygen gives us 6, and there are 2 of them. So 2 times 6 is 12, plus 4 is 16 electrons. So we will need to distribute 16 electrons around this molecule to give every atom an octet. So we start by distributing our bonding pairs. So we're bonding here, and then we can add some lone pairs to our oxygens. 2, 4, 6, 8. Uh-oh. We're already going to start to run out of electrons before we get to our octets. So what we see is that this doesn't, we have to put a double bond here in between our carbons here, or a triple bond here and a single bond here. 2, 4, 6, 8, 10, 12, 14, 16. Okay, here's our 16, but this carbon doesn't have an octet yet. So the way to give this carbon an octet is to move a pair to here and a pair to here to make double bonds like we have with this resonance structure, or we can move 1 pair here and 1 pair here. Now we have, again, the carbon will then have its full octet, and we have this triple bond and a single bond here. Which one is correct? So how do we know which resonance structure is better? Well, we are going to use this fancy bookkeeping method called formal charge. Now, this is a fictitious charge that helps us distinguish among competing Lewis structures. So in other words, we are going to try and figure out if this structure is the more stable favored one or if this one is. Now we're going to add, they're going to look like ions a little bit because we'll have a plus and a number and a minus and a number. So like if for example the formal charge on this was +2, we would write a +2 next to it. If it was a -2, we'd write a -2. That is not an ionic charge. Okay, we're not making ions out of these. This is just a bookkeeping way. We're just keeping track of electrons to figure out what charge distributions are possible and what the actual structure might be. So in order to calculate this, you have to take your formal charge, and you get that by adding, or by starting with the number of valence electrons and subtracting the number of bonding electrons plus half, and the number of non-bonding electrons plus half of the bonding electrons. So what does that look like for our 2 carbon dioxide structures? If we have our carbon, let's start with him. So carbon comes to us with 4 valence electrons. It has no non-bonding electrons, and it has 8 bonding ones. 0 plus 4, and then, so that would be 4 here, and 4 minus 4 is 0. So the formal charge on the carbon in this one is 0. For our oxygen, we start with 6. We have 4 non-bonding electrons and 2 bonding ones that we count because we have 4 non-bonding, and so half of that would be 2. So 6 minus 6 is 0. So the formal charge on this is 0. Let's look at our other side. So our carbon still has 4. It has no non-bonding electrons, and it still has 8 bonding electrons divided by 2, so that's 4. So 4 minus 4 is 0. Okay, so our carbon is still at 0. But let's take a look at our oxygen. So the oxygen on the left has 6 valence electrons, and it only has 2 non-bonding electrons, and it has 6 bonding electrons, and 6 divided by 2 is 3. So our total formal charge on this guy is +1. For the one on our right side, we see 6 valence electrons subtracting our 6 non-bonding plus 1. Okay, so 6 minus 7 is -1. Now you'll notice that the sum of the formal charges needs to equal the charge on the compound itself. And since these are electrically neutral, these are not ions, the total, if you add these all up together, is 0 for both sides. So that's how you know you've done it correctly. If your formal charge, if the sum of all of your formal charges does not equal the charge on the compound, then you've done it wrong. So, how do we determine the difference between the two and decide which one is better? The fewer the formal charges, the better. That is the number 1 suggestion. Then, if you have to have a formal charge, you want to minimize the ones that you do have. Lastly, you want negative formal charges to be on the more electronegative atom when you cannot avoid those formal charges. So this is the best resonance structure for carbon dioxide because it has the formal charges of 0. So let's look at this compound here. If you'd like to pause it and practice calculating the formal charge for these 3 structures, you may do so. So let's take a look. The number of valence electrons for our oxygen is 6, carbon is 4, and nitrogen is 5. Then we have non-bonding electrons. On here we've got 6. This one has 0, and this one has 2. And then our oxygen here, half of the number of bonding electrons, so there's 2, half of that is 1. This one has 8 bonding electrons, half of that is 4. Nitrogen has 6 bonding electrons, and half of that is 3. Okay, so we add all this up, and we get these formal charges. You'll notice that the charge on this whole ion is a -1. And so if you add up these formal charges, you get -1. Same for B and same for C. So we've done them correctly, but now we have to decide which one is the better one. So C has too many formal charges. There's no need to have a -2 and a +1 on our oxygen and nitrogen because these have fewer. Also, the problem with this one is oxygen is more electronegative than nitrogen, and it has a positive formal charge, and nitrogen has negative. So this isn't really going to be real. Again, over here, we see that our negative formal charge, again, is on our nitrogen, which is not the more electronegative atom. Our more electronegative atom is oxygen. So this will not be a very big contributor to our compound. So this one here has the least number of formal charges, and the formal charge, when we had to have one, was on the oxygen. So this resonance structure is likely to be the predominant form or contribute the most to the structure of this compound.